All right, so let's talk about logarithmic functions. This is section 3.2. Okay, for our definition for logarithm, what is going on here is a logarithm is an inverse of an exponential function. Remember our exponential function, we have 2 to the power of x equals y. And in an inverse function, what do? We flip the x and the y. So for the logarithm, we're going to have 2 to the power of y is equal to x. Okay? And that's exactly what we see going on. The similar properties that happen for our exponential functions are happening for our logarithmic function. We can go back and forth between a log and an exponential function because they are inverses and because of the definition of it. Therefore, I have log base b of x is equal to y, and I just showed you that I can write it as b to the power of y equals x, and here's an example. Okay, if I were going to write it as an equivalent exponential form, the first one is going to be 2 to the power of 4 is equal to x. Remember, it's in this circular fashion. This is your base, this is your exponent, this is your output. So for b, 3 to the power of x is equal to 9. Okay, if I'm going backwards from an exponential form to a logarithmic form, I'm going to take my log, I'm going to put my base, remember it equals your exponent, and the base of the output. So log base b of 16 equals 4. My next one, my exponent, my base goes next, and then my output. Okay, if I'm evaluating, I like to think of it like 3 to the power of something, because remember, I can express it in exponential form. So 3 to the power of something is 81. Well, what is that power, class? Okay, it's going to be 4. 3 to the power of 4 is 81. And then 36 to the power of something is 6. The only way that happens is if I take the square root of it. And I can write that exponent as a fraction. So my answer is a half. 5 to this power is 1. Well, remember those properties we talked about. Anything to the 0 power is 1. Okay, so talking about those properties, anything to the 0 power of 1 is going to apply to the logarithm. Anything to, this should say, to the first power here, that shouldn't be there. Anything to the first power is itself. So if I'm expressing it in form of logarithm, it's going to look like this. And actually, I can tie in properties 2 and 3 together. Okay, these are inverse properties. Inverse properties say because these are the same, oh, look, wrong one. Because these are the same, we're left with the exponent, so our answer is x. Because these are the same, we're left with this, and our answer is x. Notice that it applies here because there's an imaginary 1 there, right? It's implied. So inverse property applies here too, we're left with 1. If the bases are the same for the logarithms, then whatever it's next to is equal to each other. So x equals y. Let's go through some examples. Okay, so here's my first example. Because 3 is the same here and here, my answer is 15. So 15. Here, these are the same, so our answer is 3. Here, I can use properties 2 and 3 that I just showed you to the power of 1. An implied 1 is there. Because these are the same, our answer is 1. For D, I want to re-express it. I can rewrite 1/3 as what, class? Good. 3 to the negative first power. Now, because these values are the same, we're left with negative 1. Okay, so now we can use our one-to-one property based on those properties I just mentioned a moment ago. Because the bases are equal, we can say that these components are equal as well. So x plus 2 equals 8, x equals 6. When there's no base there, there's an implied 10. This is called a common log. So then we can say 3x minus 2 is equal to 11. Add 2 to both sides. Divide by 3. We got 13 over 3. I'm okay with improper fractions as long as they're reduced. This one is reduced. What I was talking about a moment ago, the graphs of logarithmic functions. Okay, remember that a logarithm is the inverse of the exponential function. So it's a reflection over the line y equals x. So notice if it's here, it gets reflected over here. If it's here, it gets reflected over here. So what's happening? The x's and the y's are being flipped. Let's explore some properties. Those properties are Remember, for the exponential, you have a y-intercept at 0, 1, so now it's reversed. For the logarithm, it's now 1, 0. For the exponential function, the domain's all reals. The range is restricted from 0 to positive infinity. Now it's reversed for your logarithm. Your domain is from 0 to positive infinity unless we do some kind of transformation. And your range is the set of all real numbers, right? So you guys see that on the graphs behind me? Then we also have increasing and decreasing graphs like the exponential. Here we look at the y's. The y's are increasing. For the inverse from values that are greater than 1, for the logarithm, it's also increasing, so that stays the same. If we have a fraction for our exponential between 0 and 1, it's a decreasing graph. The same is true for our logarithm. The y values start decreasing. Notice that the graphs are smooth and continuous with no sharp corners or gaps. Exploring some of the transformations. They're consistent, everything we've been talking about. The first one is a vertical transformation. If the plus and minus c is outside of our logarithmic component, it's move it up or move it down, however many units that is. For the next one, if it's happening inside your grouping symbol, you're moving it right or left. Right if it's negative, left if it's positive. Then we get into our reflections. If our negative is outside, then that means we're reflecting over the x. If it's inside that grouping symbol, you're reflecting it over the y-axis. Then you have your vertical stretching and shrinking, your horizontal stretching and shrinking. Let's take a look at an example. I like to start this example by graphing the parent. And I like to start by actually rewriting this as y equals log base 3 of x, and then take that, write it as an exponential form. So 3 to the power of y is equal to x. Now I'm going to go ahead and create a table of values. Notice that my exponent is y, so the values that I'm going to select are going to be for the y. So I'm going to take the exponent of negative 1, 0, 1, 2. And now 3 to the negative first power, 1/3. 3 to the 0 power, 1. 3 to the first power, 3, and 3 squared is 9. So let's go ahead and graph that parent graph here. Okay, 1/3, negative 1, 1, 0, 3, 1, 9, 2. Remember, we have a horizontal asymptote that's happening right here. Now I want to explore the transformation that occurred. What's the domain of this? From 0 to positive infinity. What's the range? Negative infinity to positive infinity. The transformations that are occurring are right 3 units up 2. So that's exactly how I'm going to move this graph. I'm going to move it right 3 units, 1, 2, 3, up 2, 1, 2. I'm going to do that to every single point. Right 3 units. Oh, I meant to put that a little bit closer because it was a third. 1, 2, 3, up 2. 1, 2, 3, up 2. 1, 2, 3, up 2. And my horizontal asymptote, my vertical asymptote also moves to right here, right 3 units. And now all I have to do is connect my points, and I'm done graphing that logarithm using transformations. Let's use that same to graph this next example. So I'm going to go ahead and I'm going to duplicate the parent, then we're going to transform it. Okay, so here's the parent. Let's take a look at our given. The negative's on the outside, so that means we're reflecting it over the x-axis. So if it's below the x, we put it over. If it's on, it stays. If it's above, it goes to the bottom. So let's go ahead and actually start transforming it. Do we move our vertical asymptote? No, because it's a reflection. So let's go ahead. This one moves up, this one stays, this one moves down, and so does this one. So this is what our graph looks like. Let's as well, and I'm going to go ahead, duplicate the parent, because the parent is exactly the same as the last 2 examples, and then we're going to transform it. Alright, the negative is happening here, so that means we're reflecting it over the y-axis. So I'm going to take the points. Anything here is moving over. So let's go ahead and actually start graphing that. So at 1/3, we were at negative 1, so negative 1/3, negative 1, negative 1, 0, negative 3, 1, and negative 9, positive 2. So now my graph looks like this. My domain is different now for this graph. Your domain, take a look at how far left you are. You're from negative infinity to 0, not including it. The range is still the set of all real numbers. explore the concept of domain. So I've been hinting at the concept of domain in the graphs that we just did. So remember, the log function reverses the domain and range of exponential functions, and I mentioned that. The range is the set of all real numbers. It was opposite for exponential functions. Why is it opposite? Why? Because they're inverses. Remember, x's and y's have swapped. The domain is all the positive real numbers from 0 to positive infinity and shifts with the horizontal shift. Or it becomes opposite with a reflection over the y-axis. Remember, the last one I just did was from negative infinity to 0. And remember, because you have a horizontal asymptote, you will never equal it, so it should not be a bracket when we're writing interval notation. It should be parentheses. So notice the parentheses being used. Example here. Here we just want to find the domain, the x-intercept, vertical asymptote of the log, and we're going to sketch the graph. So let's go ahead and do that. Let's start with the domain. How is this graph moving? Adrian? Good, 5 to the right. Because it's 5 to the right, now we're considering values from 5 to positive infinity. So the domain is from 5 to positive infinity. Okay, remember that this had an x-intercept at 1, 0 before the transformation. If I moved it 5 units to the right, where is that new x-intercept? Good. So the x-intercept, also move it 6, 0. Just think about the transformations that are occurring. Okay, the next thing that we were asked is find the vertical asymptote. Where does the vertical asymptote happen at, guys? Remember, your vertical asymptote was happening at x equals 0, so where's my new one? Ricardo. Good. I don't just say 5, it's an equation. X equals 5. And now I want to actually go ahead and graph it, so let's create a graph. Okay, so now let's start graphing what we have here. So here's my graph. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So that was to 8. So our x-intercept is at 6, 0. Right here. And we have a vertical asymptote that's happening at 5. So let's graph that. Okay, if the parent started, think about 4 to the negative first power is a quarter. So I'm going to shift that point. Remember, it's reflected. That's my exponential reversed for my logarithm. So 1/4 negative 1. But I moved it to the right 5. So that's 5 1/4 at negative 1. So about right here. Okay. I quickly sketched a point for the parent. Remember, 4 to the power of y is equal to x is for a logarithm. 4 to the first power is equal to 4. So this would be the coordinate for the parent. But we're moving this right 5 units. When I move it right, it affects x. So 4 plus 5 is 9. So another point that I could connect here would be 9, 1. So 9, 1. And now I can finish sketching my graph. Alright, so let's talk about properties of common logarithms. Okay, I hinted yesterday and in the previous sections of this video that if no base is implied in that logarithm, it's called a common log. And these properties are consistent. Okay, so notice that this is still 0, so anything to the first power is, anything to the 0 power is 1. Notice that this is also, I can think of this as inverse. Anything to the first power is itself. These reduce, we're left with these values, and that's what you see happen. Okay, so now let's talk about using your calculator. The log button, without anything expressed there, is the common log. Okay, so be careful if you're evaluating a different log base with your calculator. You have to do something called the change of base in order to use your calculator if your base is not 10. So if your base is 10, then you can just go ahead and use that log button in your calculator. So take out your calculators, let's explore it. Alright, so just make sure that you are able to use your calculator, whether you have scientific calculator or graphing calculator. that you get these solutions. I just want to point out that this is going to be something that we call change of base. And if you look over here, if you put log of -3 into your calculator, you're going to get an error. And the reason being is, think about the domain. Domain for the common log is from 0 to positive infinity, unless we do some kind of transformation. So be careful. We also have our natural logarithms. The log function with base e is called the natural log. It has similar properties and similar domains. So if you look at your calculator, locate ln, that's going to be your natural log. Okay, now let's find the similar rules apply, same concepts of the properties and same concept with the domain and range. So let's actually go ahead and do an example finding the domain, x-intercept, vertical asymptote of the natural log, and then we're going to sketch it. So let's start by finding the domain. Okay, how did this common natural log move? Adrian? 3 to the right. So that means that our new domain is going to be from 3 to positive infinity. Okay, where is our new x-intercept? Remember, we start at 1, 0 for all our logs. So Adrian? 4, 0. So our x-intercept is 4, 0. The next thing we want to do is identify a vertical asymptote. Okay, remember it starts out at x equals 0. So where's our new one? 3, x equals 3. And the next thing we want to do is actually sketch it. So let's go ahead and sketch it. Don't forget that the value of e is approximately 2.72. Let's actually start graphing our vertical asymptote at positive 3. Okay, the next thing I want to do is graph my x-intercept at 4, 0. And remember, we started off at, okay, so to the negative first power, e to the negative first power is going to be 0.3. Okay, remember that I'm reversing this because it's a log. So if I'm moving this 3 units to the right, that's going to be about 3.3. So I'm going to estimate that at 3.3, I'm at -1. Then I'm going to do the same thing for when I'm at to the first power. Okay, e to the first power is going to be approximately 2.72. So if I'm moving this 3 to the right, that's approximately 5.721. So let's go ahead and estimate that. So that's 1, 2, 3, 4, 5.72, somewhere around here at 1. And now let's go ahead, connect the points, and we're good to go. And our last example, we're going to use the one-to-one property to solve the equation. Okay, ln, the base is e. Okay, so if nothing's there, it's e. Because the bases are the same here and here, we're going to set these equal to each other, just like we did in the previous example. So x plus 5 equals 15. Subtract 5 from both sides, we get 10. Okay, here's example B. So here we have x squared minus 2x is equal to 3. Bring the 3 over and see if it's factorable. Now I want to start factoring. Here I get x times x. I have to have -3 plus 1. So my solutions are x equals 3, x equals -1. Do I stop there? Okay, please note that you must plug these solutions back into the given and make sure that it works, because sometimes you end up with an extraneous solution, a solution that does not work in the given. When I plug these back in, they both work. 3 squared, 9. 2 times 3, 6. 9 minus 6, 3. Both of them check out. I can take ln of 3 in my calculator. -1 squared, 1. -2 times -1, 2. 1 plus 2 is 3. So they both work. So my solution set is -1, 3. Is that always going to happen? No. So be careful. Make sure you plug back in. Make sure you check.